Hello, honors students. This is section 2. We are talking now about isotopes like we were, but we're looking into a little bit more about what happens when they become unstable and how do they factor into the overall average atomic mass of an element. Okay, quick review. Isotopes are formed when we gain or lose neutrons. That often happens during nuclear decay, so I'm going to talk about that in a moment, what that ultimately means. But in general, when we gain or lose neutrons, if we gain neutrons, we increase the mass of the isotope. If we lose neutrons, we decrease the mass of the isotope. Even the most common form of any substance is referred to as an isotope of that substance. So carbon-12 is the most common version of carbon. Carbon-12 is an isotope of carbon, but it just happens to be the most common one. There also is such a thing as carbon-11, carbon-13, carbon-14. All of these are different variations, but they all have 6 protons. That means they are all carbon. Okay, so that's what makes an atom, of course, like we mentioned in the previous class. Since neutrons have no charge, they don't affect the charge when they increase or decrease, but it does affect the mass. Now, we already mentioned that the average atomic mass is the weighted average, okay? So think about like your grades. If all of your assignments were weighted exactly the same, some of your grades would be much higher, some might be a little lower, it just depends, but in general, it wouldn't be a very fair assessment of the amount of work you've put in because teachers usually I try to, hopefully your other teachers try to, weight assignments that are more work as more points, okay? So the idea there, of course, being that you should be rewarded for the amount of work that you do. You should, that should be a reflection of your overall achievement or your overall grade, okay? And the same thing holds true with isotopes. If most of the isotopes of carbon or most of the particles of carbon in the world are carbon-12, then carbon-12 should have a bigger impact on the average. I wouldn't just take 11, 12, 13, and 14 and divide it by 4 because that's not a weighted average and that wouldn't give me a real good, accurate representation of what the carbon is like on planet Earth, okay? So we need to factor in the percent abundance for that particular isotope. In a couple slides, I'm going to show you how we calculate that, but first, let's talk about nuclear decay and radioactivity. All right, so when isotopes become unstable, and hopefully you guys, when you were doing the build an atom activity, you realize that there is that sweet spot for neutrons. Sometimes an atom, if it has too few neutrons, becomes unstable. Sometimes if it has too many neutrons, it becomes unstable. But there is kind of a sweet spot or a certain amount of neutrons that it needs to remain stable. If it is unstable, then it may emit particles or energy to try to become stable. So if it has too many neutrons, it's going to likely try to push out some neutrons to get to a stable state. If it has too few neutrons, it might try to, get this, convert a proton into a neutron. And some of you are like, wait, I just learned these things. Now they're turning to different things. Like, what's happening? Well, you know, science. There you go. All right, so when isotopes are unstable, the nucleus sometimes is going to, as mentioned, decay. And when it does, it releases certain particles or certain waves of energy. What we have down here at the bottom is a chart that goes through the 4 different types of decay that we're going to be looking at in our class, okay? And it does say on your notes, there is not a place for you to write this because I would like for you to write it on a separate sheet because I know some of you would get irritated if I didn't give you lines and I couldn't figure out how to put the lines in there and it's just blah. And so I wanted to make sure that you have the opportunity to do it on your own paper, or if you'd like to type it into your own table, print that out, attach it to your notes, you're more than welcome to, okay? So the 4 types of decay are alpha, beta negative, beta positive, and gamma, okay? And so alpha decay is generally going to be a situation where the nucleus has too much mass in it, and so it's trying to release part of the mass in order to become more stable, okay? When it does so, you're going to see that it releases a helium nucleus, okay? Now, we generally just write this as the helium isotopic symbol. That's usually what we're going to see in there. Sometimes you might see it with a +2 charge on the top, +2. Sometimes you might see it with a +2. Either way, it's the ejection of the helium nucleus. Helium nucleus is 2 protons, bloop, bloop, plus, plus, and 2 neutrons with no charge. Well, that's it. Okay, so it has a mass of 4, it's 2 protons, 2 neutrons, and so what you're going to see is that when that happens, because it has 2 protons in it, the atomic number is going to go down by 2, and because it's releasing an additional 2 neutrons, the atomic mass is going to go down by 4, or the mass number rather than atomic mass. I shouldn't say that. I shouldn't say that. Let's say mass number. Okay, a lot of times those words are interchangeable, but I want to make sure it's super clear when I talk about releasing protons and neutrons. That is going to decrease the overall mass number, which is protons plus neutrons. Okay, so in alpha decay, like I mentioned, that's going to be a situation where the nucleus is attempting to release mass, and so it does it in an orderly fashion with 2 protons and 2 neutrons. Okay, another example of decay is beta negative decay. Beta negative and beta positive, I'm going to put a little star under both of those, okay? Those are the really weird ones. Those are the ones that seem to defy some of the rules that you may know about chemistry already. In beta negative, what you see is that, and the hard part about this is that I've taught you protons, neutrons, and electrons, okay? When you get to college, unlikely even in AP, but when you get to college, you may see that there are such things as quarks and neutrinos and antineutrinos and all kinds of other smaller particles in an atom that make up protons, neutrons, and electrons. Because protons, neutrons, and electrons are actually built from quarks. Okay? And those quarks have little minor positive and negative charges. And so if a neutron releases a tiny particle that's negative, that means that it's going to turn into a proton, okay? Now let me draw, oh, that's not drawing. Let's draw some real quick. Let me just try to draw that really quick. Let's say we have a positive, a negative, and a negative. And this is a zoomed in neutron, okay? So neutrons have positive quarks, they have negative quarks, and if those positive and negative quarks are in the same balance, then the neutron is neutral. That's why neutrons are neutral, okay? Just like atoms being neutral with protons and electrons being the same, neutrons are neutral because quarks, positive quarks and negative quarks are the same, okay? I may not be using the perfect vocabulary here, but just kind of flow with me, all right? Now, if a neutron were to release one of those negatives, then what's going to happen is that the neutron itself is now positive. It turns into a freaking proton because it's positive, right? So if we release a negative particle, and we're going to call that particle an electron, even though it's not really an electron, it's really a very tiny negative quark, but that takes too long to say, we're just going to call it an electron, then what ultimately will happen is that the neutron becomes imbalanced between its positive and negative quarks, and so we end up with a proton, okay? So what that ultimately would look like in an equation is that the substance is going to turn into a new substance, because now it has an extra proton, the atomic number is going to go up, and so we would see that written as an increase in the atomic number, changing to a new substance, okay? And the particle itself, if it's written in an equation, would look like this. Yes, we give it an E for electron, even though it's not really an electron, it's a negative quark or whatever, but it does have the idea of having no mass, because electrons and negative quarks have basically no mass, and it has a negative charge. The other type is beta positive, a little bit easier to understand now. Same idea with the neutron, but in this case we have a proton where we have positives, and it does have negative quarks inside, even though it has an imbalance, so the positive quarks make it into a proton. Protons release positive particles, and that turns it into a neutron. So same idea. If I were to release positive particles, then I would have the same number of positives and negatives inside there, and that makes the proton into a neutron, okay? That's immediately going to give us a decrease in the atomic number, so we would see a shifting in what the element actually is. And this is that weird part where I was telling you guys that we don't usually have increases or decreases of protons unless it's radioactive decay, and then we do see increasing or decreasing in protons, okay? And not every isotope in the world undergoes radioactive decay, so don't feel like everything is just constantly exploding and releasing electrons and positrons and quarks and all this stuff. It really is a rare situation for unstable isotopes, okay? For this one that I'm talking about with beta positive, it releases what we call a positron, which sounds really fun. Basically, it's a positive quark, essentially, which would be kind of like a positive-ish electron. So that's kind of how we write it when we look at an equation. We see it as a quote-unquote positive electron. Again, I don't like saying that because electrons are negative and this is a positive quark, but because it's a similar mass, hopefully you're following along here, okay? So the fourth type is gamma radiation. Gamma radiation is not any particle, which means that really nothing changes in the atom, but it is radioactive energy. Gamma radiation is the radioactive decay that hurts us, okay? Beta negative and beta positive, if we are struck with electrons or positrons, we can have damage over time, but gamma radiation is the one that really causes damage to humans. Alpha does not at all, okay? So when we're talking about radiation and we're like, ooh, it's scary, we're talking about gamma radiation, which is not extremely common, but let's look at some equations where we might see it happen. Okay, so how you might see it in equations, and if you're asking yourself, what do I need to be able to do with this? This is the type of thing I would expect you to be able to do, to be able to look at the reactants in a problem, maybe look at what particle is on the other side, and actually see what is happening in between, and kind of fill in the blanks, okay? And we'll do that on the next slide, but here's some practice, just so you can see it. Alpha decay, again, is the release of a helium nucleus. So you can see that because it's releasing 2 protons, the atomic number for this went down from 92 to 90. And because it released a total mass of 4, the atomic mass went from 230, or excuse me, the mass number went from 235 to 231. Okay. In the next one, beta, this is beta negative decay. I didn't show an example of beta positive decay, but in beta negative decay, remember that beta negative decay means that it released a negative particle from a neutron to change it into a proton. So a neutron releases a negative and turns into a proton. Okay, and so that's what happened here. Our atomic number went from 92 up to 93. The mass number didn't change because a neutron and a proton have the same mass. So just because a neutron turned into a proton, it didn't mean that I added any mass to it, so the mass number stays the same. This becomes an isotope of neptunium instead of an isotope of uranium, okay? Because now the mass number is the same, again, so the mass number didn't change, and that helps, and that should be visible because the particle that it released has no mass, so the mass shouldn't change. The particle it released did have a charge, which is why the neutron changed into a proton in this particular case. And remember that beta positive decay is when a proton changes into a neutron. And so in that case, we released just this electron-esque particle, which we can call an electron, and that's okay. But hopefully, those of you that care a little more can, in the back of your head, remind yourself that it isn't really an electron, it's a negative quark, but it is an electron by charge, so we're going to stick with that. Gamma decay, in gamma decay, the substances really should be the same. Nothing should be changing because even though this energy is released, it doesn't change the mass or anything in the particles, so we really shouldn't see any major change there. Okay, let's practice this really blurry slide really quick. All right, so looking at this, I have a reactant of lead 196, and it has 82 protons. What I see on the right side is that I have thallium, which has 81 protons, okay? So what I know is that a proton has changed into something else, okay? And so if a proton changed into a neutron, a proton disappeared in this case, or quote-unquote disappeared, proton changed into a neutron, so what that means is that this is an example of beta positive decay, okay? And so I should see an electron with 0 mass and a positive 1 charged particle, okay? Because essentially, that proton releases that slight positive charge and turns into a neutron, so my positive number went down, okay? In the next one, we have another example of beta positive decay. So I have phosphorus 28, and it is undergoing beta positive decay, which means that a proton is turning into a neutron, so I should create element 14. The mass does not change, and element 14, I believe, is arsenic? Hold, please. Silicon, yes, I said silicon, right? That's exactly what I said. Yeah, okay, yeah. So phosphorus has a proton that turns into a neutron and becomes silicon. Okay, in this particular case, silicon-28. In the next example, I have radium-226 with an atomic number of 88 and a mass of 226. On the right-hand side, I have radon with an atomic number of 86, which means that it went down by 2, and a mass number of 222, which means it went down by 4. Hopefully in your head you're like alpha, 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 alpha decay. It wouldn't alpha decay. Helium, 4, 2. Yay. Okay, so really what you're trying to do is find the missing link. What is the puzzle piece that's missing in this case? If it goes down by 4 and 2, then it was missing a alpha decay particle or a helium nucleus. In the last one, I have zinc. Zinc-73 with 30 protons. And on the right-hand side, I have zinc-73 with 30 protons. What is the only decay that I told you that really doesn't change the atom? Gamma decay. Okay. Gamma decay is kind of like a sloppy Y, and then it has 0 positive charge or 0 charge, 0 protons. It has 0 mass because it's just energy. Okay, I'm going to slide through this slide pretty quick, so make sure you're following along. Average atomic mass, basically we're going to multiply the mass of each isotope by its respective percent abundance, and then we add up the totals. Let me pause really quick, move the slide, and then I'm going to show you how it's done. All right, we're ready. So the way we do this, if we're calculating average atomic mass, and in this case I'm going to say it's of carbon, of course, because we're looking at carbon. These are two different isotopes of carbon, one with a mass of 12.000 and one with a mass of 13.000. The percent abundances are on the right. First thing we need to do is get our percents into decimals. So divide them again by 100. I don't know why it looks like 1100. By 100, okay? That's going to give us, for the first one, 0.9890, and for the second one, 0.010. Nope, 110. Okay? So when I go to do this calculation, what I want to do is have 12.000, so my first mass, times the decimal of that abundance, 0.9890, close parentheses, because that's all carbon-12. That gets added to the other carbon, in this case carbon-13, 13.003 times its percent, 0.0110, close parentheses, because that is carbon-13. If I had more, I would keep adding and doing the exact same thing, but in this case, I don't. Okay, so what I can now do is perform this calculation. 12 times 0.9890 is 11.868 plus 13 times 0.0110. 0110. Yes. No. 13.003 times 0.0110. I was looking at that. I was like, that don't look right. 0.143011. Okay. Now I'm not rounding these at all yet. I'm putting down exactly what my calculator is telling me. Then going to add those two together. 11.868 plus 0.143011. And I get a value of 12.011011. What's my last step? Yes, thank you. Sig figs. Yeah, thank you. I heard you. Okay, all right. So in the problem, it looks like my lowest sig fig, I'm just going to look at my masses because percents are usually just rounded however we feel like a lot of times. So I'm going to look at my masses. My sig figs is 5. So I'm going to do 1, 2, 3, 4, 5, 12.011 AMUs. Okay, AMUs is the atomic mass unit, so that's the unit we use for averaging atomic mass. Okay, I'm going to go through this first one again with you guys, and then I'll give you the answer for the second one, and you can work through that one on your own. All right, so for the first one, if we're calculating average atomic mass, I'm going to take the mass of the first one. In this case, it's just going to be a rounded whole number. That's not extremely common, so don't always assume that it will be. But we're going to take 35 times 0.7500 Add that to 37 times 0.2500. I would keep adding if I had more, but in this case I don't. So I'm going to do this all in one calculation in my calculator so that I don't have to do it more than once. 35 times 0.7500 plus 37 times 0.2500. And I get a value of 35.5. According to my sig figs, 2, 4, 4, 2. I'm going to go with 2. So this would be 36 AMUs. Okay. Bottom one, like I said, pause it. I am going to give you the answer for that one. So run through that one on your own, please. And then unpause it, check your answer, and then we'll go through some more. All right, you ready? I'm giving you the answer now. Second one, AAM. I got 13.6. Check my sig figs. 3, 3, 3, 3. So I'm going to go with 3. 13.6 AMUs. Here it is worked out a little bit more, and yes, I don't want to talk about it. I rounded my sig figs wrong. It's 36, okay? So you can remind me that if you ever make a mistake on your sig figs, I'm still going to count off for it, but you can remind me that I made mistakes too, and I made it in a video for everyone to see, and oh well. All right, moving on. So in your notes, it asks you to do a summary. I would like for you to do a very specific summary. So what I'd like to see is for you to discuss what makes isotopes different from neutral atoms, how they're formed, and then discuss how they factor into the average atomic mass for an element. I will see you guys next time. Oh, also, don't forget to do your practice problems. Okay, bye.